Hello students. So today we will discuss the geometrical interpretation of the upper and lower sums. So in last class we have seen the definition. So let us note that if fx is greater than or equal to 0 for every x in AB, then the lower sum LPF can be interpreted as the sum of the areas of the rectangles with base xi minus 1 to xi and height mi. Mi was the infimum of fx in the interval xi minus 1 to xi. Similarly, the upper sum UPF can be interpreted as the sum of the areas of the rectangles with base xi minus 1 to xi and height mi, capital Mi, that is the supremum of f in that particular interval. So let us have a look at this diagram. So this is the diagram that we have for the lower sum. So this is the interval AB and this is the function graph of the function f. So this is a function f defined in the interval AB, and we have a partition x0 x1 up to x5, and so the minimum value of f in this first sub interval, as you can see from the graph, is this. So with that minimum value as the height, we construct a rectangle whose height is that minimum value and width is the length of the interval x0 to x1. Similarly, for x1 to x2, we construct a rectangle with width x1 to x2 and height given by the minimum value of f in that particular interval. So here you can see in the graph, this is the minimum value of f in that interval. Similarly, for x2 x3, minimum value of f in this interval is this value. So we construct a rectangle whose height is this minimum value and width is x2 to x3. So similarly for x3 x4 x4 x5. So this area, the sum of all this area of these rectangles is actually the lower sum. And similarly the upper sum for each interval, we will take the maximum value, that is the supremum of f in that particular interval. So as you can see, for this first sub interval the supremum is this. For the second sub interval, this is the maximum value of f. So we construct a rectangle whose height is this maximum value and width is x1 to x2, and similarly for the others. So that way this represents the upper sum, the sum of the areas. So from the diagram you can clearly see, we have already done that as an exercise, that LPF for any partition, LPF is always less than or equal to UPF. So you can see this area, the sum of these areas is less than the sum of this larger rectangles. Each of these rectangles are larger in height or greater in height than the corresponding rectangles of the lower sum. So LPF is less than or equal to UPF. We have already proved that, and here we have demonstrated. So we can make use of the software Sage Math that we have already done in practicals to illustrate this lower sum and upper sum. Say we consider this function f(x) equal to x square plus 1 for all x belongs to 0, 1. It is an increasing function, as you can see. If you take the derivative, then it's twice x, which is always positive in this interval. So it's an increasing function, and hence for any partition p x0 x1 up to xn of 0, 1, the infimum of f in xi minus 1 to xi is actually f of xi minus 1, and the supremum of f in this interval is f of xi. So therefore small mi is this f of xi, and your capital Mi is this f of xi. Small mi is f of xi minus 1 and mi is capital Mi is f of xi for every I. So to illustrate this in Sage Math, we take the case of particular partition, that is the equally spaced partition that we have already done in our higher secondary classes when we started with integration. So there we used to take equally spaced partition. So for that, xi will be actually xi minus 1 plus h. H is the length of each sub interval, so which is constant. It is b minus a by n. So in this case it is 1 minus 0 by n, that is 1 by n. So if we write this following the Sage code, p equal to empty graphics and fx equal to x square plus 1, then you plot this function fx equal to fx from x equal to 0 to x equal to 1, and then take p equal to p plus p1. Then you take the value of n as 10 and h equal to 1 by n. So we are constructing a partition having 10 sub intervals, and you can see this command that we have already done. So we are plotting the function. So we are plotting this. The function is constant function y equal to f of I. We just need to plot the rectangles. So that is what we are plotting. And the function is already plotted in this particular command. So we are plotting the rectangles, and then similarly for upper sum, this is the code. I'll show you in the Sage Math software itself. So let us have a look in this Sage Math software. So this is the file. So here is the file. So this is an illustration of lower sum with the increasing function fx equal to x square plus 1 in the interval 0 1 using equally spaced partition. So here you see, if we take n equal to 10, so in that case there are 10 equally spaced sub intervals, and this is the illustration of the lower sum that we have already defined. You can change the value of n and see what happens. So if you take n equal to 5 and press shift enter, so what is the changes? So these are the things. So the number of intervals decreases. So, and suppose you increase the value of n further, say 20, so you see you get a different approximation. So the area under this particular curve is better approximated by increasing the number of sub intervals. As we increase the number of sub intervals, the area under the sum of the areas of these rectangles and the area under this curve, they become close to each other. So here for n equal to 20 we have taken this. So if you see the error, the difference between the area under the curve and area under the rectangle decreases. If you take 2 here, or say 5 here, the area under the curve is and area under the rectangle show a large difference. See, this is the difference between area under the curve and area under the rectangles. Okay, so if we increase the value of n, we get a better approximation of the area under the curves. So this is the lower sum, and you have already seen in higher secondary classes that we take n tends to infinity in the definition of the definite integral as a limit of a sum. So that is a particular case of this Darboux's integral or Riemann integral. So similarly, you illustrate the upper sum using the increasing function fx equal to x square plus 1, the same function. So if you see, I have plotted it for n equal to 5. This is the upper sum. The rectangles are above the height of the rectangle is above the curve. So if we take 5, it's like that. If you take say 20, in that case the heights of the rectangles becomes lesser. So we get a better approximation. See, we get a better approximation in this particular case. So as you increase the number of sub intervals, or in terms of this mesh or the norm of the partition, if we decrease the norm of the partition, decreasing the norm of partition is equivalent to increasing the number of, in one sense it is equivalent to increasing the number of sub intervals. So say if we take say 50 subintervals, in that case what happens? See, we get a much better approximation of the area under this particular curve. And so this actually motivates the definition of the upper integral and lower integral. As we increase the number of subintervals, you see the upper sum, increasing the number of subintervals is actually taking a refinement. So if we take refinement, the lower sum increases and the upper sum decreases. So at some point we can expect that the lower sum and upper sum will become equal to one another. If that happens, then the function is said to be Darboux's integrable, equivalently Riemann integrable, which we will see after a few lectures. So this was the illustration. You can relate this with whatever we have learned in the first lecture. So in the next video that I'll upload, I'll define the upper integral and lower integral using this concept.